A year ago, no one could ever imagine that a new deadly disease was going to spread all over the world, changing people's lives drastically. With over 3 million deaths worldwide, the governments from every nation decided to restrict any type of activity in order to stop the spread of the virus. This left remote communities isolated and helpless as they lost communication with the mainland. Therefore, during the current academic year, we have designed a UAV to provide aid against COVID-19 to those remote places. Along with some other specifications, the key requirements will be to transport a payload of 130 grams over a range of 10 miles and be assembled by remote engineers within 2 hours. Happily, we can see that our UAV has accomplished its mission.
This is one of our initial early designs using an airfoil shape as a fuselage. We soon moved on to a fixed wing design with a square fuselage and an empty tail. Naturally, at this point, we pretty much thought we'd nailed it, and a conversation went something like this before our first ever test flight. To that shocking display, we were back to the drawing board. We improved the design in several ways, increasing the spacing between the rear tail supports and also increasing the amount of glue used to affix the wing structure. It was our intentions to mount an aft-facing propeller. However, from flight testing we realised this would be too dangerous since the aircraft had to be hand-launched, and ultimately the rear-mounted tail design of 2 laminated struts was simply not possible. It created flutter and vibrations during testing, and also was very easily snapped off. We then moved on to our next design iteration.
The next design has been improved over many different aspects, one of the 2 including the reinforced fuselage connecting the horizontal tail, which with this implementation provided a higher structural integrity and also a reduction in the total aircraft weight. Secondly, the addition of dihedral wing tip devices, which increased the rolling stability, really seen the benefits during the flight test stages. And with a single fuselage design, which is manufactured from a single piece of foam board folded from a net.
We then went on to perform a glide test for this new design, and as you can see, it was pretty successful.
For our final design, we chose a modular structure with a hinged design for an easy loading, transportation and assembly. As well, it mounts a set of flaps and a larger vertical tail for stability at low speeds. The payload is fitted at the back of the fuselage, while the front includes a battery fitting for a quick replacement.
Number of avionics systems on board our aircraft which enable it to fly. There are 6 servo motors which are responsible for the movement of the control surfaces. One is located under the elevator, one by the rudder, and there are 2 on each wing, one on the aileron and one on the flap. There is a gyroscopic sensor which measures the aircraft's orientation. This sensor communicates with an Arduino Uno which houses the autopilot function. The Arduino communicates with the gyroscopic sensor and the servo motors in order to autonomously maintain level flight. There is also an electronic speed controller, which is responsible for controlling the motor speed and therefore the aircraft speed. All of the avionics on the aircraft are powered by the battery.
Prior to flight testing, a flight test plan was created and shared upon the group. Flight tests were always conducted within the CAA regulations. With pinpointed boundaries prior to flight, it provided a safe operation for everyone involved.
Several tests have been performed to assess different flight parameters against key performance indicators. Thanks to a camera mounted on the tail, as well as a GPS, it's possible to determine speed, height and position at any time. Different flight configurations, such as flaps deployed, are useful to check stall speed and low speed maneuverability. The main objective of this flight was to assess the autonomy of the aircraft, while verifying data such as maximum speed, climbing rate and glide ratio. After executing the different exercises, some low speed approaches were done to locate the best landing area, and after 40 minutes and 17 miles flown, it was time to land.
In conclusion of the flight testing, it can be said that the aircraft has a sufficient flight envelope. In addition to this, the aircraft succeeded the capability of flying with the required payload amount of 130 grams. Furthermore, the aircraft proved itself dynamically, providing a stable flight throughout. Thanks to the design and test stage of this project, we have sufficiently met all the requirements to its mission.
Further improvement in terms of autonomous navigation capabilities is needed. The communication between GPS and Arduino to allow waypoint missions is still to be implemented. This upgrade will lead to the final product in around 80 work hours.